Okay, today we want to start off and talk a little bit about this model that we talked about before, but now we'll give it a little bit more thorough treatment, but the production possibilities frontier, the production possibilities curve. Just want to sort of explore that. It's really a richer, fuller model than what we've given it credit for so far. And so anyway, let's get that up here. If you remember the definition of a production possibilities curve, it shows combinations of two goods that can be produced using all available resources. And do you remember we talked about what the resources were before? The land, labor, capital, and entrepreneurship. I won't go through that list again since we have talked about those before. But let me draw you a graph that would, I think it's just the graph that we had up here before. I drew a straight line like this. Good X and good Y. We're talking about units of good X and Y. And the point I made is this, is if we use all available resources and produce only good X, we'll produce XM, or let's call it X max. Yeah, that could be like a new store chain, couldn't it? X max units of good X. Okay? If we instead took all of our resources and put them only into producing good Y, we could get Y max units of good Y. And then we can vary the resources half and half, 2/3 and 1/3, but we can vary the resources between these two goods and produce various combinations of the goods. Okay, so anyway, there's our production possibilities frontier. Let me put some actual numbers here rather than X max and Y max and so forth. And let's call these computers and televisions. Computers and television sets. That's supposed to be a straight line. So we've got in this horizontal direction number of computers, and of course if we're talking about a national economy we might be talking about 5 million rather than just 5, but the units don't make a whole lot of difference here. And we've got, what do we have here, 10 units of television sets, 10 million or whatever you like to have. And then what we can do is we can see these combinations of the various goods that we can produce. I'm not the best artist. I'm not even in the running for the best artist. Anyway, the point is, though, is that if we take all of our resources, I'll say again, and put only into computer production, we could have 5 computers or 5 million computers or 5 billion, whatever the number would be. If we take away just 20% of our resources, take away 20% of our resources from computers and instead put those in television production, then we're going to have 2 or 2,000 or 2 million, whatever the number is, but 2 units of television sets. And we've cut back our production of computers slightly, and we've increased our production of television slightly as we move from let's call this point A to point B. And as we move from point B to point C, what we've done is we've sacrificed one more computer. We've taken away the resources to produce that one more computer, and we instead put those in producing televisions, and so we get 2 more televisions. And so it goes as we move our way up the curve. Each time we're losing 1 computer, and each time we're gaining 2 televisions. right? Minus 1. And so point E, we've lost one more computer down from 2 to 1, and we got 2 more TVs from 6 to 8, and so forth down to 0 and 10. Okay, so now what we've talked about before is the term opportunity cost. Along this particular production possibilities frontier, production possibilities curve, we give up one computer to get 2 TV sets. This is also the slope of the curve, isn't it? The slope of the curve is 2. We talked a little bit last time at the end of the hour about slope. But what I told you to do is, if you've got a line, pick 2 points on the line and look at the horizontal distance and the vertical distance between the points. And here's B and C, if you like to think about that other curve. Here's computers and TV sets. Okay? And I told you that the slope is equal to the rise over the run between those 2 points, the vertical distance divided by the horizontal distance. And so what we would have here is the vertical distance is 2 between the points, and the horizontal distance is 1. So the slope is 2 over 1. So one computer has the same cost as 2 TV sets. Right? If you want to get one computer, you would have to give up 2 TV sets. Or if you want to get 1 TV set, we can divide here. 1/2 computer is equal to 1 TV set. So the cost of 1 TV set is a half computer. The cost of 1 computer is 2 TV sets. Let's see, 2 computers equal, that's not right. 1 computer equals 2 TV sets. So it depends on what we want to talk about in terms of its cost, but if we're interested in the cost of 1 computer, the cost of 1 computer is 2 TVs. If we're interested in the cost of 1 TV, it's a half computer. It's the slope of this line will tell us that. Questions about this? Stop me if you want to talk about any of this. Okay. Now, here's what's significant. This is a straight line. We want to talk about that for just a second. It's a straight line as straight as I can draw it. We want to talk about that for a second, why it would be a straight line. Let me draw another production possibilities curve that's not a straight line. Let's put something like wheat and houses. If we use all of our resources in society to produce only wheat, we get some maximum amount of wheat. If we instead take all the resources away from wheat and just put it into producing houses, construction industry. We've got farming and construction, don't we? But if we do that, we have some maximum amount of production. And then suppose that we vary our resources between them. Some of our resources into producing wheat and some into producing houses. We'll have some curve that looks like this one. This one is, and let me just kind of jot this up here, concave to the origin. Meaning that if you were standing here at this 0 point, this origin, looking up, this curve would be, looks sort of like a cave to you. You'd be looking inside of it. It's concave toward the origin. Another way of saying it is it's bowed outward, away from the origin. It's bowed out. You can describe that in either way. But in this one case, we've had a straight line production possibilities curve. In the other case, we have a production possibilities curve that's either bowed out or concave toward the origin. What's the difference? Well, the difference is this. Here we were talking about 2 things, computers and TV sets, that use a lot of the same technology, a lot of the same skills, the same kind of factories, the same kind of assembly line workers, a similar, did I say technology, but in terms of developing microprocessors and so forth, very similar types of technology here. And so if you take away resources from producing computers and put those resources into producing TV sets, they work pretty well. Maybe just a little bit of retraining, they do just as well producing TVs as they did producing computers. But here what you have is the skills. You need a lot of land to make wheat. You need a lot of rainfall. You need certain types of skills. You need tractors, of course. Certain types of skills of the farmer out here on the farm to grow the wheat. Those resources, the land, the water, the farming skill, the tractors, those resources aren't the kinds of resources that would normally be used to manufacture houses, to construct houses. Those would be different. And so what we have in a case like this is that the resources to produce wheat are not as effective at producing houses. Okay, so in this particular case, since our resources are not equally well suited to producing both goods, they're not equally well suited to producing both goods, then we get a curve that looks like this one. And I'll talk more about it in just a second, but so far, you know, all we want to do is relate this idea to the nonlinear production possibilities frontier. Okay? And it's due to the fact that these two different goods use different resources, vastly different resources in their production, whereas in our earlier case they use very similar resources or the same resources. Okay? Now, let's talk about opportunity cost in this particular case. Let's suppose that we start off at this point right here, and we're using all of our resources to just produce homes. And we say, I want to get, this much wheat. I want to get 1 unit of wheat. And so I have to take resources away from producing homes. I'm going to take some builders, some carpenters and so forth, out of home production and send them over and tell them to produce wheat. Now, you know which carpenters we'd take out of home production. They're the ones that probably shouldn't have been there in the first place. Farmers who we had taken them off the farm and put them out here manufacturing houses, building houses, they're the first ones that would say, you're kind of awkward around a house and around a hammer and so forth. You don't seem to know what you're doing, but you're an awesome farmer, so we're just going to send you to the farm. And so when we take this guy or guys and we take them away from the construction business and send their tractors out to the farm because we're saying, yeah, we've been using your tractor around the construction site a little, but it hasn't worked out that well. When we start shifting resources away from home production over to wheat production, then what we notice is that we get a little bit fewer homes, but just slightly. We're going to lose home construction just a little bit when we try to increase our wheat production, when we move from point A to B. We're just barely going to have to give up some houses, and the reason for that is we have moved our most awkward carpenters out of the housing construction business onto the farm. And they were better farmers than builders. And so in terms of what we have to give up in terms of houses produced, not very much. And we get this unit of wheat produced. Okay? Let's say that we want to do this again. We want one more. I'm going to try to make this the same amount here. We want one more unit of wheat, 1 more million tons or whatever you'd want to call it. We want to move to point C. We've actually already taken our most awkward carpenters, the best farmers, out of producing homes. We've already moved them over into producing wheat. That was our first move, moving from point A to B. Now that we move from point B to C, we're taking some people away from housing construction that are a little bit more good, a little bit better carpenters, not more good, a little better carpenters and not quite so good at farmers. And so when we try to increase production of wheat by just that one more unit, what we notice is construction of housing goes down again, but it goes down by more than it did previously. In the first instance, we only had to give up this tiny amount, units of houses, in order to get the wheat, the 1 unit of wheat. But when we wanted 1 more unit of wheat, we had to give up more houses. Let's go to the opposite extreme. I'm going to try to get this distance and come back to right here. Let's say this is, 10, so then we'll go to 9. Suppose we were already at the point where we were producing 9 units of wheat. This is point, I'll call it D. We're already producing 9 units of wheat, and we want 1 more. What we do, if we want more wheat, we have to take some more people out of producing homes and move them into the farming business. But now what we're doing is we've gotten all of the really awkward carpenters. We already moved them out of this business, the people who are better farmers than carpenters. And now for us to get a little bit more wheat, we're moving people into farming that are terrible farmers, and they're really good carpenters. And so when we increase our production of wheat by 1 more unit, look at the amount of housing that we have to give up in order to get that 1 more unit of wheat. It's a huge amount. So what's the conclusion? The curve has this appearance due to the fact that resources are not equally well suited to producing all goods. That's why the curve has that shape. And then when we have a curve that does have this particular shape, bowed outward or concave to the origin, when we have that shape, then let's talk in terms of opportunity cost. At first, the opportunity cost of wheat is very low. And then as we get a little more wheat, the opportunity cost of wheat went up a little bit. And so it continues to go up until out here at the very end, if we want 1 more unit of wheat, the opportunity cost of getting that wheat, what's it cost us? What do we have to give up in order to get the 1 more unit of wheat? A huge amount of houses, a huge number of houses. So what we have is we have increasing opportunity costs. In our earlier case, we had constant opportunity cost. If you want 1 more unit of televisions, you would have to give up 1/2 unit of computers over and over and over. It'd just be that constant cost. But here the cost is increasing. The more wheat that we get, the more it's costing us. The first amount of wheat costs almost nothing. This last unit of wheat costs a huge amount. We see that graphically by the shape of the curve, but the cause of it is the really important thing. Resources are not equally well suited to producing all goods. That being the case, opportunity cost is going to rise the more of this good that we want. Now, what's the lesson here? The lesson I see is that we're going to have increasing opportunity costs if resources are not equally well suited to producing all goods. In real life, do you think resources are equally well suited to producing all goods? Usually not. I can do certain things better than other things. I can teach economics better than I can paint the house. I can teach economics better than I can do plumbing. I can teach economics better than I can do almost anything. And that's sad. I know that you've seen how I teach economics, so if I'm worse at everything else, that's a very sad commentary, isn't it? Anyway, in real life, I'm saying I think that most of the time resources are not equally well suited to producing just various goods. And so in real life, we're going to deal with production possibilities frontiers with this shape. And in real life, we're going to face increasing opportunity costs. If we as a society want to produce more cars, we can produce some more cars, but the more cars we try to produce, the more expensive it will be to produce them, the more costly it will be to produce them, not in terms of money, but in terms of the other goods and services we have to give up in order to get them. Really what we're talking about this is when we start specializing in producing things, and we do specialize in our society, when we start specializing in producing things, and resources are not equally well suited to all things that way, when we specialize, resources are a little bit less adaptable, a little less versatile in terms of being used on other things. That being the case, one of the things that we just face in our society is this situation of increasing opportunity costs. Okay, any questions about this? Constant cost, increasing cost. Probably the increasing cost case is the most realistic. I would urge you, when it's time to study for a test, I would urge you to work through these numbers just a little bit and make it clear to yourself where I was talking about these opportunity costs. What we have in each one of these instances, just moving between any 2 points, is 1 computer equals 2 TV sets. That's between any 2 points. That's the slope of this curve. And now, to know the cost of something, all we have to really do is, well, here we've got the cost of 1 computer has got the cost of 2 TV sets. If you want it to be, the cost to be expressed in terms of TV sets, divide by 2 on both of these, and so you get 1 TV set, and its cost is 1/2 computer. So that's how to work out these opportunity costs, is simple math. We'll come back and do a little bit more of that in a few minutes. But first, let's go on and talk about a few lessons that the Production Possibilities Frontier illustrates. The first lesson, we can distinguish between attainable and unattainable regions. Let me draw this curve again. What's attainable? What's unattainable? Here's what is attainable. With the resources and technology available, we can produce at any point along the Production Possibilities frontier. We can produce at any of those points. All of those points are attainable. What about this point? This point, I'll call it A, that's underneath the Production Possibilities frontier. Is that attainable? Sure. We can produce more than that. We can certainly produce that much of X and Y that are shown by this point A. Okay? So really what I'm telling you is this, is everything along the Production Possibilities frontier is attainable. We can attain all those with our resources and our technology. We can attain every point under the Production Possibilities frontier. The points that we cannot attain are points outside. The things that we cannot attain and the things that we cannot have are combinations of X and Y lying beyond the Production Possibilities frontier. Okay? How about this? I'm going to put another point here and call that U. I'm going to say that that's a point of unemployment. So we can distinguish what's attainable, what's unattainable, and what's happening when we have unemployment. When we have unemployment, we have resources that are not working. This curve, the frontier itself, is showing us the maximum amount of these goods that we could have if we used all of our resources as efficiently as possible. And if we're not using all of our resources, then we have some unemployed resources, and an example would be like that point U that I've labeled right there. We have resources that are just not working. We have people not going to work. We have machines that are not being run however many hours a day they were designed to be run. We have land that's not being put into use, and so forth. So anyway, the Production Possibilities curve, it contains these ideas. We've already talked about another idea, scarcity. Talked about that a few days ago, but the idea of scarcity is to be at some point like this. We desire to have a huge amount of all goods, really. We'd like to have a huge number of TVs and computers and houses and cars. We desire to have a huge amount, but we're not able to attain all that. Let me just kind of get these things out of here. And if you remember what I said the other day is this condition that we have where that our desires exceed the resources available to produce goods. We'd like to have more than we actually can have. That's the idea of scarcity. We cannot have as much of things as we would like to have. Opportunity cost is illustrated by this. by this diagram, by this model. And if you remember, we just talked about that one moment ago. Just pick a couple of points, point A and point B. And opportunity cost, the cost of getting this little bit of extra X is how much of Y that we have to sacrifice in the process. So opportunity cost is the slope of the curve, as we said just a moment ago, moving from one point to another on the production possibilities frontier. So it illustrates that concept. Choice. Choice is illustrated by this. The idea is we would like to be out here beyond the production possibilities curve, but cannot be. And so what we have to do is we have to choose. If you can't have what you want, if you can't have everything you want, what will you choose to have? Let me draw the curve again, and all I'm saying to you is you've got to choose some point along that curve. Where do you want to be? Do you want a little bit more of good Y? Do you want a little bit less of good Y and more X? Choose. The necessity to choose is there because we cannot attain all that we desire. And that being the case, we have to decide what's most important to us. And finally, the idea of efficiency is illustrated. What do I mean by efficiency? Well, what I mean by efficiency in this particular instance is I mean getting as much output, as much production as possible from the resources available. Let me create a point A right here. Let's make a point B there. What I want to show you is that point B is not efficient. And here's the way I go about that. If we started off at point B, what we would have there, let's say 5 units of good X and 5 units of good Y. I'm just making up the units, of course. But we'd start off with 5 units of each good, and I'm saying that's not efficient because it's also possible for us to produce at point A. It is on the production possibilities frontier. It's possible for us to keep the 5 units of Y and move over here and have, let's say, 7 units of good X at this combination. And so if we can have more of good X without giving up any of good Y, that means that we were not producing as much as was possible with the resources that we have. And if we're not producing as much as possible with the resources we have, we're using our resources inefficiently. We can simply get more out of our economy than we are getting out of it at point B. So point B is a point of inefficiency, and point A is a point of efficiency. Questions about any of this? Let's go on and talk about economic growth. This is another idea that can be illustrated with the production possibilities frontier. Let me draw the first production possibilities frontier up here, and I'll just label that A prime. That shows how big our economy is, how productive our economy is. Economic growth would appear like this. And I'll say B prime. In this particular instance, economic growth just appears as a production possibilities curve that's shifting outwards. We can have more of good X, or we could have more of good Y, or actually we could have more of both. So the concept of economic growth shows up in our production possibilities frontier as just a curve that is shifting outward. Boy, if we had something, and we talked a moment ago about unattainable, if we had some point out here that was unattainable before, that was unattainable before, now that point becomes attainable with economic growth, something that we could not have in the first instance. Maybe this is the 1980 production possibilities frontier, and this is the 1990, let's make it the 2000 production possibilities frontier. Something that in 1980 we would have just said, you know, this is impossible. We cannot be at this point out here. Can't do it. Wish we could. Well, then by 2000, 20 years later, it was possible. And so economic growth is shown in this diagram as just shifting the production possibilities frontier outward. How fast does the U.S. economy grow? Does anybody know? We'll talk about that subject more later on in the semester, but in the neighborhood of 2 to 3% per year. That's how much the U.S. economy grows. And I'm talking not about the dollar value of what we produce. I'm talking about physical production of goods and services. We're able to produce 2 or 3% more cars and more clothes and more houses and more of everything, really, each year, about 2 or 3% more than the year before. This is kind of a good time to do it, so let me just give you a little mathematical formula. I'm going to call this the rule of 72. The rule of 72 tells us how long is required for a variable to double in value. I also want to put up here that this is a rule of thumb. And I don't know why they say rule of thumb, but it's not right out to 6 decimal places or anything like that. This is pretty close. Okay, and here's how the rule of 72 works. 72 equals R times T, where R is the annual rate of increase in the value of the variable. And T is time in years for the variable to double. So let's come up here and use 3. Suppose that I tell you that the U.S. economy is growing at 3% a year. 72 equals 3 times T. Now what we have is we have one unknown. Once I've told you that the economy is growing 3% a year, then what we can do is we can solve for that one unknown, the T. This becomes 1. This becomes 24. Are you with me on this? Simple math. And here's what that says to me. T, the time in years for, here it's the size of the economy, to double is 24 years. At 3% growth a year, every 24 years, the economy would be twice as big as it was before. Okay? So if our economy is, I'll just pick out a number here, if our economy is $9 trillion in size right now, and if it grows 3% a year, then 24 years from now, the economy would not be $9 trillion in size, it would be $18 trillion in size, twice as big. Now, we can use this in a lot of different ways, and that's one of the reasons that I wanted to mention that early on. You can use this for yourself. Let's say that you've got an income of, you go to work for $25,000 a year when you graduate from college, and your income is growing by, well, let's say 6% a year. I'll just kind of jot that up here. What did I say, $25,000 a year? And it's growing, I said, 6% a year. How long until you're earning $50,000? Well, we could come back up to this formula and say 72 equals 6 times T. Divide by 6. This becomes 12, doesn't it? So 12 equals T. 12 years later, you'd be earning $50,000. Make sense to you? Let's say that you had $100,000 invested in the stock market, and it's growing 18% a year. Now, not that you can count on the stock market to go up 18% a year, but suppose it does. You've got $100,000 in the stock market's going up 18% a year. Where's a good place to write? 72 equals 18 times T. You divide by 18. Help me out here. 4. In 4 years, your $100,000 would become $200,000. You get it? So you can use this rule of thumb, and I'll see if I can't get an opportunity for you to use it on test day. But this rule of 72 can be used really for a large number of applications, but one of them is this thing that we started off here talking about, which is how rapidly the economy is growing. Let's say the economy is growing, we said at first 3% a year, then we said every 24 years the economy doubles in size. If the economy grows at 2% a year, you know, that doesn't sound like much, does it? 2%, 3%, who cares? But if the economy is growing 2% a year, it would take 36 years for the economy to double in size. Not 24 as before, but now 36. And so you might think, yeah, 2%, 3%, those sound like about the same. They're not that much different. It makes a big difference in practice. It would make a big difference in practice whether your stock market investment was going up 18% a year or 12% a year. 18% a year, every 4 years you double your money. 12% a year, it's every 6 years. And so forth. So anyway, now back to our story. We want to talk about economic growth. What causes this to happen? Why does the economy grow? Just because it has to grow? No, it doesn't have to grow. Is there something just built into economies that make them expand? No, there's not. There's a lot of economies around the world that do not grow. So what makes an economy grow? Normally two things. One, more resources. And I mean by that, we've got more land, labor, capital, entrepreneurship, a growing number of resources, or two, better technology. Fortunately for us, we're living in an era when technology is improving rapidly. But anyway, more resources or better technology. If we have more resources, you know, the shape of the production, or I'm sorry, the position of the production possibilities curve to begin with was based on how much land, labor, capital, and entrepreneurship do we have available. And now if we had, let's say, 10% more of those resources, that production possibilities curve would shift outward by about 10%. Now, let's go down through the list. Land, labor, capital, entrepreneurship. Land, are we going to get 10% more land from one year to the next? Seems unlikely, doesn't it? So if we're not going to get, and maybe I ought to make my list up here again of these resources, land, labor, capital, and entrepreneurship. Entrepreneurship, that's a French word. If we're not going to be getting 5 or 10 or 20% more land, that doesn't seem to be a source of economic growth. We could go and conquer Canada, and then we would have a little bit more land, but in terms of world economic growth, that wouldn't help. We haven't created land. It would just shift it from Canada to the United States. I don't think we're getting ready to conquer Canada, so that's not really in the cards. I don't think we're getting ready to conquer anybody. Anyway, but I'm saying to you, land, that's not really going to be a source of growth. We're not able to accumulate much more land. You know, in Holland, they would go out into the ocean, build a dike, pump the water back out over top of that dike, reveal the land underneath, and they produced a little bit of land. And also, we don't want to forget that when we say land, we mean all those natural resources. So it would be possible that we would clean up the air, get rid of some of the pollution in the air, and then we'd have more clean air. Same thing with the water and so forth. So we can clean up some of these resources and have a little bit more, but this is a tough go. I mean, it's just not an easy thing to have 5 or 10 or 20% more natural resources. And so that's not going to be a source of growth. How about labor? Is the labor supply, is the labor force, is that growing? And the answer is, yeah, it's growing a little bit. Not rapidly. The labor force grows about 1% a year in the United States, more or less, but that's just a ballpark number. It can be a little more, it can be a little less. About 1% a year. On the other hand, you know, or maybe you don't know, I know, that in a number of countries, Spain, Portugal, Japan, Italy, in a number of countries today, the population is not growing. The population's kind of stabilized, and if you look out 50, 75, 100 years, a lot of countries are in a situation where the labor force and the population can be expected to go down, not up. Let's take the United States, though, just in our case. Let's say the population and the labor force are growing 1% a year. That is going to be a source of economic growth. This curve would shift outward about 1% a year if we have 1% more workers. Here's the bad news. At the same time we're able to produce 1% more goods and services, we have 1% more people to share that. And since we have more people to share in what we produce, on a per capita basis, on a per person basis, we're not really experiencing much economic growth. It's more a case of, yeah, we've got a bigger economy and we got more people to share it with, and we're all about the same off in terms of our well-being as we were before. So what I'm saying to you is the growth in the labor supply is a source of total economic growth, but in terms of per capita growth, per person growth, not really. Capital and entrepreneurship. This entrepreneurship is largely one of ideas. You know, the entrepreneur is the one, we talked about the entrepreneur the other day. The entrepreneur is the one who says, here's what people would like to have, blue salt. I think I talked about that the other day. Blue salt. It's an idea. I think people want this. They stop me on the street and ask me about it. They say, Tom, when's that blue salt thing coming out? And I say, you know, it's very soon now. We're doing some tests over in Europe. Anyway, these are ideas. Can we have more ideas? Oh yeah, we can have ideas. There's not a limit to that. Entrepreneurs are the source of economic growth, or a source of economic growth, because it's just these ideas that bubble out of people's head, and then they said, I'm going to put that into practice, and they go out and start up a company and do it. How about capital? And the answer is, there's not a very tight limit on the amount of capital that we have. We can produce capital from natural resources. There's a lot of natural resources out there. I'm saying that it's not easy to cause the amount of natural resources to grow, but there's still a lot of natural resources out there. We can take a very small amount of natural resources and turn it into capital goods. And so these things right here, capital investment and entrepreneurship or ideas, those are the sources of our economic growth. Now, capital would include things like computers, warehouses, dump truck, or a delivery truck, hammers. And that's a few examples. I'll stop listing them. A capital good, and we're talking about something physical, something tangible here, but a capital good is a good that has been produced by people, and it's used, in turn, in the production of other goods. And so I'm saying these things right here, computers, warehouses, dump trucks, hammers, those things have been produced by people, and then those things are used to produce other things. Right? And so we can accumulate capital goods, and then that will be a source of economic growth. We have a lot of capital goods investment in the United States, and in the last 10 or 15 years, a lot of that has been high-tech kind of investments, more computers than warehouses or dump trucks. And so, yes, we do have economic growth from that. And entrepreneurship, you know, we can't do a whole lot about putting new ideas into people's heads, but what we can do is we can influence people to take those ideas and run with them, do something with them. Take it from an idea and put it into action. And one way that we can encourage people to do that is we could give them lower taxes on their profits. If you go out and start up the Blue Salt Company and you make $1 million from it, we won't tax that. We'll just let you keep the $1 million. Well, that would be a real inducement. If instead we said, you start up the Blue Salt Company, you make $1 million, we're going to tax 75% of that away, then I'm thinking, well, if I made $1 million, I'd only keep $250,000. Now, that's a lot, but I'm going to take a lot of risk also. If people don't like the Blue Salt idea, then I lose everything I invest. And so the more favorable we make that outcome, if I get to keep everything as opposed to only keeping a quarter of it, then I'm much more likely to put that idea into practice. And so that's really what we're talking about here, is putting the idea into practice as opposed to, I've got an idea. So, and let me mention one other thing, human capital. And economists actually include that as a capital good. So I want to mention it especially just so that you're comfortable with that term. Human capital is basically this. It is investing in the worker, the laborer, to make that worker more productive. Human capital, you guys are investing in human capital by going to college. You go to college, you learn skills you didn't have before, and now your labor services are more desirable than before to an employer, and so your pay is going to go up. You're going to be more productive. Your pay is going to be higher as a result of going to college. But there's a lot of other things you can do to build human capital. You could take a night class learning how to run a particular computer software program. You can also build your human capital by just having a job and working and learning skills. So there's many different ways of building human capital, but the point is that human capital, and education is the sort of general term that we talk about, how people build human capital. Human capital affects our economy pretty much the same way as getting more computers and so forth. We're simply able to produce more in the way of goods and services than we could in previous years. And so then capital and human capital plus entrepreneurship, those are going to be the sources of economic growth. One final thing, and then we'll stop for the day. How are we going to accumulate capital? How are we going to make this happen? How are we going to push that curve outward? Well, accumulate capital. Here's how to do that. I want to draw another production possibilities frontier, but I want to label the axes slightly differently. Consumer goods, capital goods. Let's start off at point A. We're using our entire economy, all of the resources, to produce only consumer goods. Cars, TV sets, stereos, VCRs, you know the types of things I'm talking about. We use everything to produce consumer goods. We produce no capital goods. So now what happens is we just have a fixed amount of capital. It's however much capital we had on hand at the beginning of the year, that's what we have at the end of the year. We're not accumulating capital. And so this production possibilities frontier stays right where it is. Let's say that we do something like this instead. We move to this point B. We give up some consumer goods. And when we do give up consumer goods, we take those resources. We were going to produce cars, let's say sports cars, and now we take the resources away, land, labor, capital, from producing sports cars, and we put that into producing computers, let's say. Capital goods. Now we have a lot of capital goods. We're accumulating capital goods. We're producing capital goods that we didn't have before. As a result of producing these additional capital goods that we've done moving from point A to point B, this curve shifts outward. We now have more capital, and capital now becomes a source of economic growth for us. The economy is growing due to our investment in capital goods. Now, that's the good news, is we know how to create economic growth. Here's the bad news. In order to create economic growth, we have to invest in capital goods, and that means that we have to give up consumer goods. So if we want the economy to be bigger next year than it is this year, what we have to do is give up something this year. We have to give up some consumer goods this year so we can produce the capital goods and have a bigger economy for the future. You remember I gave you that term, that TANSTAFL. There's no such thing as a free lunch. We can't have economic growth for free either. If we want economic growth, we have to give something up. It has an opportunity cost. We give up consumer goods now in order to have a bigger economy in the future. And let me take it back again to your level, and mine too. I went to college here. But you right now are giving up something. You could be out earning an income rather than going to college. You give that up in the short run in order to accumulate human capital in order to have a higher income in the future. And that's what I'm saying the U.S. economy can do as well. That's where we'll end for the day, and I'll see you next time. So long. Well, I thought we'd take a few minutes here after class to talk about graphs a bit. Normally we use graphs in economics every day or two in class, sometimes a number of times, and so we don't want to get very far into this until you're comfortable with the graphing, sort of understand why we do it and where I'm coming from. We use graphs normally for a couple of reasons. One is to display data, and so let me sort of draw you a graph or a chart and give you the idea. The first time that we display data, let's just put time on the horizontal axis and something like just an economic variable, let's say gross domestic product. Or sometimes we call this GDP. We'll put that on the vertical axis. Gross domestic product is the broadest measure of economic activity in the United States. It's basically all the new production, the value of new production by everybody in the United States. So what we might want to do is come back to, let's say, 1960 and find out the amount of gross domestic product. And in 1960 is along the horizontal axis. We're measuring time here, years and so forth. And then we could come up to the vertical axis and put a dot that represents gross domestic product in 1960. And I'm not exactly sure what that was, but let's say in today's dollars, maybe that'd be 850 billion, or it would probably be more than that. But let's just use that number, 850 billion, and then we could come along from 1965 and 70 and so forth, working our way forward. And we would find the amount of gross domestic product each year and put a dot on the chart to represent that. Now, let's say we have a recession in 1980, maybe the economy turns down, and then by 1985 it's growing again. Then we could come along and connect the dots. You've probably known that game since you were a child, but connect the dots and show basically how the economy has performed through time. And so this is the first thing that we might do with charts and graphs, and also how you may see charts and graphs used in magazines, newspapers, and so forth, is to display data. A second kind of display we might have is where we don't put time on the horizontal axis, but another economic variable. Let me draw us another graph, and along the horizontal axis now I'll put, again, let's say gross domestic product. So I've moved that off my vertical axis to the horizontal. And on the vertical axis, let's put consumption spending. Now, just as we did before, we could go back and find out the amount of gross domestic product over the years. We could go and find out consumption spending over the years, and then each year we have a combination of the two. So, for example, if we got 1960 data, we might find that gross domestic product was, I used the number before, $850 billion, and we might find out, for example, that consumption spending by households, maybe we would find out that's $700 billion, and then we put a dot right here to represent that combination of income, gross domestic product, and consumption spending. We do the same thing for other years. Each year we ought to be able to have a different dot. We'd have a different amount of gross domestic product, another amount of consumption spending. And so normally what we would expect is that as gross domestic product goes up, as people's income is greater, then they're going to spend a little bit more. And we may see a relationship something like this. Again, just connecting the dots to get the idea of it. We see something like this. My straight line isn't too good, but you get the idea. Now what we're doing, again, we're displaying data, just as we did in the first diagram. Now in the second one, we're displaying data, but in this particular case, we're showing a relationship between variables. These variables we think should be related to each other. We think that because of the economic theory, which we'll get to later on in the semester. And so now what we're doing is displaying both bits of information, one related to the other. And what this diagram would show me is that as gross domestic product rises, and therefore people's incomes rise, that they tend to spend more. Let's go ahead and use that as sort of a springboard to talk about the third type of diagram that we will use. And really this third type of diagram is what we'll use the most. We'll just use the graph to depict the theoretical relationship between variables. In this previous chart that I just did a moment ago, we started off with some numbers that you could get out of an economic publication or from the internet and so forth. But in this particular case, what we might do is just come along and say, you know, I think that there is a theoretical relationship between gross domestic product and consumption spending by households. And now we're not going to actually get the numbers and put dots up here, but we might just draw a line that looks like this. Again, this is a graph, but we might just display a line like that to depict this relationship. And that line, we've got a formula that goes along with it. Consumption spending equals, and now we'll have a number like this, $50 plus 0.8 times gross domestic product. I'm going to use the letter Y to stand for gross domestic product. But there will be a formula that describes this curve. And the formula or the curve, they have exactly the same meaning. And you know, some people are comfortable with formulas. Some people are comfortable with looking at the curve, the graph of this relationship. Of course, a third thing we could do is actually create a table where that we would say, you know, if income is zero, then this formula says that consumption spending would be $50 plus 8/10 of zero, so consumption spending would be $50. 8/10 of zero, of course, is nothing. If income was, let's say, income or gross domestic product, $200, then consumption spending would be 50 plus 0.8 times 200. Well, 0.8 times 200 is $160, plus 50 is 210. Let's try one more and then we'll stop. If gross domestic product was $400, then consumption spending would be 50 plus 0.8 times 400. Well, 0.8 times 400 is 320, plus 50 is $370. And so now what we have is three different things here, and you can see all three. The one is the diagram, the curve that shows this relationship. Second thing is a formula which shows the same relationship. And a third thing, we've got a table that shows that relationship. And some people are more comfortable with the numbers, some people are more comfortable with the formulas, and some with the graph or the line. There's, of course, a fourth way of representing this relationship, which is just verbally. And we could say, consumption spending is a positive relationship to income. As income goes up, consumption spending goes up. That's not quite as precise as these other methods that we have, but these are all different ways of communicating about this. What we will see a good deal of this semester is the curves themselves, which show a theoretical relationship. Usually we will not be working on the numbers that go with it. Usually we will not write down the formula. We will just put the curve there that represents the relationship that we're talking about in class. You want to be sure as you're going along and not get confused by these diagrams. We'll have a lot of them, and as soon as you find yourself getting confused, that's the time to come see me or come see the department tutor or work in the study guide. But you cannot let this get ahead of you, because there will be literally hundreds of diagrams before the semester is over, and you're going to have to understand those diagrams as a way of representing the theories that we talk about in class. You'll see some more of these in our lecture tomorrow, and so let's stop for the day and just go along with that. So long.